Yes, welcome to this session in the pedology in soil landscapes and spatial mapping space. We've got a few talks this afternoon, and the first speaker is going to be Linda Lilburn from Manaki Whenua in New Zealand, and she is going to talk about adding geomorphic context to SMAP via soil landform trees.
Right, good afternoon. This is a project that started about 3 years ago with my co-authors there. But there are a few other people that have contributed over the years as well. David Lowe, Alan Palmer, Peter Almond, Peter Singleton, Phil Tonkin and Andre Eager. What are we trying to achieve with it? It's this explicit capture of soil surveyors' knowledge. The users of this are the soil professionals, primarily. But we also see a use for land managers and those in education as well, wanting to teach or learn about soil pedogenesis or pedogenesis. Applications is around remapping in the future. So where we've got a soil survey's been done, it's really important to capture that knowledge so that when someone in the future comes back to this area to remap it, they've got access to all of that knowledge from the original surveyor. And of course also into, if we've got an area and we're mapping in a new adjacent area, it's really helpful for that soil pedologist surveyor to access the knowledge from a nearby area. Another application is downscaling. So what is SMAP? This bit's really for the Australians, because the New Zealanders all know what SMAP is, and they're all nodding, so they do. It's New Zealand's Soil Information System, started back in 2004. Now, New Zealand is hugely variable in its soil forming conditions and the consequent spatial distribution of the soils. And for that reason, we've made SMAP a hybrid. It's a bit of a horses for courses type situation. So we do have polygons and map units, but we also have grids. We have the traditional ways of doing things where the covariates are not available or it's really unpredictable. But we use the digital soil mapping methods where we do have the predictability and we do have the good covariates. So we're trying to do the best we can for what the landscape offers us and use the best methods. We do have some manual data entry, but we also have the pedo transfer functions, and they range from really simple rule-based models through to quite complex statistical empirical models through to the machine learning. SMAP is really widely used throughout New Zealand, and one of the really big drivers of that is the nutrient budgets and the need for the freshwater outcomes, so budgets for N and phosphorus, used for irrigation consenting as well. The big thing that we started in 2004 was getting that national soil correlation throughout New Zealand. That soil taxonomy is what underpins SMAP. So where you have a soil that's functionally the same here, and it's over here as well, then they have the same name. They're treated as being the same soil, even if they're on different locations. So the Wakanui is an example that you'll find down on the flats, but you'll find it now up on the hills, which of course wouldn't have happened in the old days. The problem with SMAP is that we've lost that geomorphic context, because a soil survey map is actually a lot more than the taxonomic similarity, which is what it's capturing now. It's the result of the pedologist's mental model of the soil landform relationships. And so what I wanted to do was explicitly capture that knowledge in a database so that we could reuse it for a multiple of purposes. Essentially, it's the information that used to be in the soil bulletins that we no longer produce. So we started on this, down this route of defining a landform tree hierarchy. These are the levels in the hierarchy. So at the top, we divvy it up into land provinces, and they are trying to express the really large-scale lithology, the tectonic regime, the climate differences. You see the scale on the right-hand side, that's where it's aiming in terms of the variation. Next level down, the regions, and that's the lithology-based macro relief, and may cover a range of climates, or it may be separated by climate regime. Now the sub-region, we've put that in as an optional level, because sometimes where it was really complex, we found we needed to aggregate or be able to separate things out a wee bit more. So we put the sub-region in there as well. Tends to pick up lithology in the response to erosion or sediment generation, storage and flow. The land system is something that you'll be more familiar with. It's starting to identify that place where you get the recurring patterns of topography, rock-type lithology, with or without the cover beds. Beneath that's the land unit, and that's where we're trying to identify the sequences. So it might be a topo sequence, a litho sequence, climo or chrono sequence. And the land component is the parts within that sequence. There is another level below that called the land element, but that's sub-polygon level, so it's not on this table. So there's what looks like for the North Island provinces. So remember, that's the top level of the tree, and this is the current depiction of what that will look like. I'll talk a little bit more about that central North Island area in a moment, and then the South Island is there. So I'm just going to dive into that middle one in the South Island, what we call the front ranges and inland basins. Hopefully you can read that. So first of all, it's just divvying up. This is Trevor's work, and he's separating out the front ranges, the inland ranges, and the inland basin. So that's at the region level. And below that, he has used the optional sub-region, so he's identifying, separating out floodplains, terraces and fans, moraines, downlands and hills. Then we can go into the next level. So the green is getting into the systems. And you can see there under terraces and fans, he's separating out the terraces and the fans, but he's also using age, whether it's an old or younger or very old surface, to then identify his different systems. But you see that's different to the moraines, where he's looking at whether there's a cover bed of loess or not. And in the downlands, it's becoming more the parent rock that becomes the divider of the different land systems. And then down a level again, he's then picking up on the soil moisture regime primarily to separate out his land units. So what does that look like spatially? So what we've got here, it's a bit in the Waitaki Basin. You've got the Southern Alps to the northwest of this picture. And so the closer you are to the Alps, that's when it's wetter. And so you've got the green, which is more the wetter soil moisture regime, going through to the yellowy, orangey, through to the orange, which is the driest. And each one of those soil moisture regimes will have a different combination of soils in them. Let's go up a level into the land systems in that Waitaki Basin. And you can see there we've got the blue, which is the wetlands, coming out to the floodplains, which are in the yellow. The sort of orange, the browny kind of colour is the young terraces, through the greens, through the ages, through to the, there's a little bit, does it work? See a mouse? No, you can't see a mouse. So downlands, and then round the edge of the lake you've got the moraines. So you can really see that pattern of soil genesis there. You can see how the soils would have changed with the landforms. Moving now up to this area. So let's look at where we are now in the Waikato Basin. So this is a diagram that picked up from David Lowe has used in his lectures. So it has got the old soil series symbols on it, but we'll ignore that for now. What it is the Hinura Formation is a fan deposit that's infilled from an eruption approximately 26,000 years ago from Taupo, which is to the south of this area. And the distribution is very much explained by the geomorphological features of this formation. So we've got I wish I could point or had a pointer. Can't do anything about this, I don't think. Okay, so we've got the channels and the swales that we can see. What's about how to do this? So the gullies are coming in from the top right, the middle right. So we get the gullies incising this deposit of the Hinura Formation, and then we have the levees and the bars and that kind of yellow. That's the Horitu soils. We have the channels and the swales, which are in the white, which are the Te Kōwhai soils, and in between was a kind of where the BR and the SSR. That's sort of kind of the in between. They're a bit of leve bar, bit of channel. Can't really distinguish them. What we're calling there the mix, the Hinura surface. And then we've got the peatlands, which is where the drainage has become blocked up. The water is formed there. It's become a swamp, a wetland. and over time the peat soils have developed. So that's the pedogenesis of the area. How do we then take that into our tree, a landform tree? So that's what it looks like. The blue is the channels and the swales. We talked about the gullies. You can see those with the purpley colours, the levees and the bars there, and the bits with not much colour, the sort of beigey colour, are those ones that are a bit of a mix of the two. Onto the left, you've got the low hills, and the X is where we are right now, those of us in New Zealand, well, those of us here in person, in the Waikato University. And the peat is in the grey. So when we look at the tree, what Scott has done with this work is he has divvied it up into this is the northern lowlands, so he's divvied it up into the basins and plains. Within that, you can see that there's a Hanura formation, sort of second little yellow one down. And then within that, you can see the surface, and he's divvied it up to the Hanura surface and the peatlands. Within the Hanura surface, he's capturing the levees and the bars, the channels and swales, and the gullies. The hills are in the next bit further down, in the purple bit, where it's a cover bed with tephra. So you can see all of that knowledge that Scott has got in his head about how that soil is formed is now being captured in that tree. This is showing another bit. This is this new province that we're thinking about just at the moment. It's what we're calling a central North Island tephra, because we've got this deep tephra that goes right across the middle of the North Island. And so we've got our volcanoes, Taupo to the south, it's got these deposits, and as you are closer to the volcanoes, it tends to be pumice. As you come further away, again to the allophane, so that's the pinky purpley colour on the lower part, it's more the allophane tephra, and as you go further north, it becomes more weathered, and it becomes more granular, and then further away, ultic soils. So there's quite a strong pattern there that we want to capture, and so we're thinking about doing a tree for this, and this is the way that Scott has divvied it up, so you can see the proximal, the distal and the weathered, doing that distance away from the volcano, and then he's picking up whether it's deep or discontinuous, and then the different soil within that. So we're still looking at this, because you can see from the next slide, which is maybe a little hard to see with the colours, but it's quite widespread, this tephra layer, and it really overlays across everything else. So we've got the brown is the northwestern sedimentary hills, and we've got the beigey colour, which is the northern lowlands, and the pink is this potential new tephra layer sort of spreading its way across, sitting across the top of these deep tephras. So we're still thinking about this. Some examples of outputs of these trees is if we're in a location, say we're on that gully that we were just looking at, we can go up the tree. And so that first bit there is showing that we know that we're on the gully, that sits within the Hanura surface, that sits within the formation, that sits within the basins and plains, and that in turn sits within the lowlands proper. Each of those can have a short description, or it can have a great big long description. And that can include all sorts of diagrams. It can, if it's describing the unit level, then that would just be a sequence. So you might just have a 1D diagram, you might have a 2D diagram for the systems, or 2.5 to 2.5. Annotated photos. You could even put audiovisual clips into this. We can have the pedologist explaining what the land system is. We can put that into the database, pull it out on the fact sheets. So there's a wealth of information that we can make available. Obviously, we can automate the link to what the soils are. But also, we can go down the tree as well. So we can start with a geographical area and then pull out all of the trees and all of their branches that are relevant to that particular region and auto-generate the reports that describe the pedogenesis in that area. So that's where we want to head. In terms of the future, we still need to do a little bit of work on just refining some of the bits of the classification. It is quite an iterative process. We start at the top, we work our way down, look across, no, that doesn't quite fit, go back up, change it. So we're still working on that, and probably that North Island central tephra layer is our key one that we need to work through. It's important, if I'm going to automatically use this data or auto-generate reports and maps, it has to be consistency between the different trees and the provinces, but between the different levels as well. So that's what we're looking for. We need to populate it. We need to develop the templates to then auto-generate these maps and fact sheets and reports. And then I think the next question, which is very important, is how can we then use this knowledge in combination with the more data-driven approaches and in models? And I think hearing Tom Bishop this morning, one obvious case of this is using it to define the, I forget what he was calling it, but basically the area by which you can extrapolate to, the area of something, AAA or whatever it was, so AOA. So I think this is going to be really useful for that because the podologist knows about those changes that make it valid or not for any modelling. So that completes. Andre?
Thank you, Linda, for this very good talk, and I'm certainly happy to see the landforms back in SMAP or in the SMAP too. We've got. I can't see any questions in the app, and I guess we can then go to the next speaker. It's a virtual presentation from Dongxue Zhao about clay content mapping.
Hello everyone, I'm Dongxue Zhao, a PhD candidate at UNSW, and today I'm going to present a study on clay content mapping and uncertainty estimation using the model averaging techniques. Clay content in the topsoil governs the soil fertility, buffering capacity, and biological activities for around 60 to 80% of the roots of most crops. And in the subsoil, it determines the storage capability of soil moisture and nutrients. So the information of clay is needed for soil quality assessment and decision-making in land use. Digital soil mapping method has been used for clay prediction, in which proximally and remotely sensed digital data is coupled with observed clay data. In terms of digital data, proximally sensed electromagnetic induction, EM, remotely sensed gamma ray spectrometry, digital elevation model, and slope have been used. This is because they are directly correlated with the soil clay content. Although this digital data have been used, the importance of them for clay prediction at different depths needs to be assessed to provide insights into the scope and factors, which can be used for generating digital soil maps of clay. In terms of models, various models have been used to couple the clay data and digital data at different scales, ranging from the linear mixed model to the various machine learning models. Whereas there are seldom studies systematically compare the performance of these models on the prediction of clay at a district scale using both proximally and remotely sensed digital data. And in addition, each model has its own strong and weak points. When prediction of clay is dominated by one single model, there is a high chance that aberrant prediction would be made. So instead of selecting the single best performed model for one given condition, combining prediction outcomes from several models into one prediction outcome through model averaging techniques could be considered for clay prediction. So in this study, the aim is to generate digital soil maps of topsoil and subsoil clay at a district scale by comparing the importance of proximally sensed ECA data and remotely sensed gamma ray spectrometry DEM and slope data, and also by comparing individual performance of models, including a linear mixed model and various machine learning models, including the skill-based random forest support weaker machine, QRF, XGB boost, and back earth. And also by comparing two model ensemble techniques from the top 4 models, including the GRA averaging method and the least concordance with weights averaging method, and also by comparing the prediction uncertainty of each calibration model and model averaging techniques. This study was conducted in a 39,000 hectare area in the Brizza Plain, New South Wales, Australia. In this area, a wide variety of parent materials and soil landscapes were found. The western margin of the area is formed from sandstones and isolated outcrops of Carboniferous volcanics, and the eastern quarter is defined by the Carboniferous geology, and in between the alluvial clay defined the Leopold Plains. And the climate in this area is semi-arid climate, and soil use is irrigated cotton and grazing. 2 types of EM instruments, including EM38 and EM34, were used to collect the soil ECA data at 867 survey points. And the gamma ray data was obtained from Geoscience Australia based on a gamma ray radiometric survey. And the DEM slope data was obtained together with the gamma ray data. In total, 70 soil sampling locations were selected based on the EM survey, and the soil samples were collected from 0 to 1.2 meters with 30 centimeters increments, and the soil particle size fractions were determined using the hydrometer method in the laboratory. For the calibration of models, the linear mix model consists of fixed and random components. The fixed component represents the spatial variation of clay explained by the digital data, and the random component represents the unexplained spatial variation. And the parameters of linear mix model were determined based on the residual maximum likelihood using the GOR package. And for the machine learning models, train function from the carrot package was used to optimize the parameters for each model. The top 4 calibration models were selected for the model averaging based on the independent validation results. And the principle of model ensemble is to combine outcomes from different calibration models by the weighted summation. And the GRA fits a multiple linear regression in which measured clay is regressed against the corresponding predictions derived from the top 4 best model. And the least concordance weights averaging decides the weights for each single model based on the validation least concordance of this model. To calibrate each model, 70% of the available soil samples were randomly selected as calibration data set, with the remaining 30% used for validation. And to avoid the inflation on the goodness of fit during validation, 50 iterations were conducted for each type of model. And to assess the uncertainty of the clay prediction at each depth, 90% prediction interval from the 50 iterative predictions of each model was calculated based on the 50 times validation and predictions. The spatial distribution of gamma ray total count indicates that smaller total count coincided with the Leopold Plain, which can be attributed to the lack of radial elements in the alluvial clays, while larger total count was in the western and eastern margins. due to the radioactive parent materials in these areas. For the EM38 ECA data, a generally inverse distribution of the total count was observed, in which larger ECA data was found in the Liverpool plains due to the heavy clays. And in contrast, the smaller ECA data was in the western and eastern margins due to the sandy soil. Equivalent patterns were also observed for other channels of EM data. In addition, the larger slope was found at the location of western margin, in which the steepened hills were there, and the smaller slope were associated with the flat Liverpool plain. The variable importance from random forest indicates that Gamma data was most important for topsoil clay prediction. This is because the 90% of Gamma measurements are generated from the radio elements in the topsoil, the top 30 centimeters, and there are large correlations between the type and number of radio elements in the soil and parent materials. In the subsoil, the slope was most important, which was likely due to the distinctive geological features in the study areas, namely the rolling hills in the western and eastern margins, and the more flat alluvial plain in the center. So validation list concordance shows that, in general, the random forest performed the best for clay prediction, followed by Q-based QRF and linear mix model, and after performing the other three models for all the depths. And in addition, the prediction accuracy decreased with the soil depth, which suggests that the digital data explain more variation in the topsoil than in the subsoil. It also shows that both model averaging approaches improve the predictions, regardless of depth, comparing to consider each model individually. That the GRE improved the prediction more pronouncedly. Similar trends could also be observed on the prediction interval, in which model averaging reduced the PI value in both depths, with GRE more pronounced. Here is the predicted clay content in the topsoil and subsoil using GRE. They are consistent with the distribution of landscape units in this study area, with larger clay content in the Liverpool plain and smaller clay in both eastern and western margins. In addition, the maps of prediction interval shows that the prediction uncertainty was larger in western and eastern margins at both depths. This is because the diverse landscape units and low sampling density were observed in these areas. It can be concluded that Gamma data was most important for topsoil clay prediction, while in the subsoil, slope was most important, followed by Gamma, ECA, and DEM. For the topsoil clay prediction, the random forest was best with fair accuracy, followed by QRF, Q-based, and random forest, and after performing the other three models. For the subsoil, all 7 models achieved poor prediction accuracy, with random forest being the best. Both ensemble methods improved the clay prediction and reduced the prediction uncertainty in 2 depths, with the improvement using GRE being more pronounced. At the end, I want to acknowledge my all the support from my team, UNSW Soil Science Central, and also acknowledge the RTP scholarship for funding my PhD. Thank you for listening.
John can relay that. Very good, thank you. And then we move on to the next speaker. Tom South is going to talk about the optimal mathematical model and sample size to map CEC in a sugarcane field.
Hi, this is Tom, and I'm very happy to join this virtual meeting. And it's a little bit pity that I couldn't join the in-person meeting due to the lockdown in Sydney. Okay, today I just want to introduce my research work. The title is The Optimal Determination of Mapping CEC, that means cation exchange capacity in a sugarcane field. In my study, I will use CEC, that means cation exchange capacity, using of the electromagnetic data and gamma data with different comparison of different mathematical models, sample size, and survey data, and transect spacing. With all these results, I'll put some discussion on line application in this field. Okay, before introducing the CEC, I think we all love sugars. Let's start from a sugar party. I think we all love the candies, donuts, but I think the sugars are from the sugar canes. There are two different ways for the fertilizing here. The first one is the ordinary ways. You see, it's always labor cost and time consuming. In our modern society, we need a more advanced technology. But there's a question: how much fertilizers do we need? Before introducing the technique, I will just give a brief introduction on the CEC. What's the CEC? CEC means the cation exchange capacity, because usually for the soil minerals such as the clay particles and soil organic matters, they are usually negatively charged. This negatively charged surface is always with strongly and supplying plant nutrients such as the potassium, sodium, calcium, magnesium. This charge, the positively charged, is called the cations. The process of uptake and the removal of cations from soil solution by clay particles and or in soil organic matter is termed as the cation exchange. Cation exchange capacity of soil is then defined as the total sum of exchangeable cations that it can absorb, including the sodium, potassium, calcium, magnesium, and aluminum. Value of CEC in this range can indicate the presence of naturally swelling clays such as a semi-type. But how about for farmers? For farmers, they need samples of CEC determination, so appropriate or moderate rate can be determined. And in our sugarcane industry, there is just something like Bibles. It's called the 6 easy steps. Yes, it's just like its name. There are 6 easy steps. The first one is knowing and understanding the soil. The second one is understanding and managing nutrient process and losses. The third one that we need to do for my study is regular soil testing. The first one is that with our results, we need to adopting soil-specific nutrient management guidelines. What's this guidelines? It's just in this table. That means for different CEC rates, there are different line application. And for the 5th and 6th steps, it's just in the future work that it should be tested for other stuffs. But there's also a question for the soil sampling or just soil testing, because when getting CEC value is always time consuming and money cost. There are different steps. The first one, we need to collect soil samples. You see here, you'll see we always need some straw men to collect samples. And after we collect the core samples, we need to crush them. And even after get the crushed samples, we need to get the dilution. And for this machine, there are usually 23 samples for a batch, and it will usually take us around maybe 1 day to get sometimes 1 day to get the dilution. But it's not finished. After getting the dilution, we need to do some element analysis. It usually takes around maybe 2 minutes per samples. But this is most expensive part in some cases. But we have some much easier ways. It is called the digital soil mapping. It's just like a bridge. We may use some proximate data to get the soil to predict soil property. What are the ingredients? The proximate data, including the electromagnetic data and the gamma data. Why? Because for the electromagnetic induction data, this time we use the Julian 421. We can detect different depths of the soil, such as for 1 meter beacon, it can detect up to 0.6 meters, and for 4 meter HCON, it can be deep as the 6 meters. And even for gamma ray data, because there will be some emission of the gamma ray from minerals, so theoretically it can detect the topsoil from the 0 to 0.3 meters. Okay, after we get the ingredients, we need to get a brain to build this bridge. What it's called? It's called machine learning, or just in regression, because machine learning is quite popular recently. Machine learning is an application of artificial intelligence that provides systems the ability to automatically learn and improve from experience without being the specific program, specific experience. Machine learning just focuses on the development of computer programs. And this time we just use 5 models, including QBIS model, random forest, spot vector machine, linear mixed model, and the regression creating. Okay, my aims for my study is that in a sugarcane field like those in the first line, can we use ancillary data, that means the gamma ray data and the Julian 421 electromagnetic data, to map cities in different layers in an easy way with the optimal mathematical model, the sample size, ancillary data, and transact spacing? Okay, our field in Proserpine is in the central part of the Queensland. And for the soil samples here, we just collect 160 samples for different depths, including 0.0 to 0.3 meters, that is topsoil CEC, and 0.6 to 0.9 meters, that is subsoil CEC. For the ancillary data, we just collected 23 transacts with 5 meters apart. Of course, the data types, just including the Julian and Julian electromagnetic data and the gamma ray data. And in the soil type here, it includes the chromosol, curosol, water soil, candy soil, and soda soil. And we can see that in the north part, the CC is quite low, and in south part, it's getting higher for the top. This is for subsoil, and even it's similar for topsoil. And for the EM and the gamma ray data, they have similar trend. That means lower in north part and higher in south part. And to do some comparison, we just do the separate validation. That means we separate the 106 samples into 2 groups, one for validation with 40 samples, one for calibration with 120 samples. Because we will just do some analysis of different soil sample size, then we just use the CLHS method to choose samples from the 100 until 10. And for transect spacing, because its original transect spacing is 5 meters, later we just compare 10 meters, 20 meters until 18 meters. Before doing modeling, we just need to the or to choose which components it's better for us to predict. With backward regression, we just choose the potassium 1 meter beacon, 1 meter HCON for the topsoil prediction or just modeling, and for also potassium total count 2 meter beacon, 4 meter beacon for the subsoil modeling. Okay, let's see the results. For topsoil, we can see that when we use both ingredients, including gamma ray and ion data, the QBIS model is usually best, and especially when the sample size is 80, it already can reach the least concordance can reach around 0.6, and it has similar results for the root mean square. We can see that it has lowest root mean square among these models. However, when we only use the gamma ray or EM individually, their performance are not good as the both components choose. And for gamma ray, the QBIS is also the best when the sample size is around 0.8. But for EM, the linear mixed model is the best. And once we just get to predict with the QBIS model with both components and the sample size of 80, we can see that they have the similar trend as the measured samples, but there are more details revealed here. For the subsoil, it has something similar. That means for the qubits are also best when both components, but this time we could only choose 30 samples are enough for the subsoil. And with different transect spacing, for topsoil, we had to say that we need to use original transect spacing, but for subsoil, the 60 meters part is fine because it has higher length concordance and better performance. After we get the results, we can just apply 6 easy steps. In this case, for the topsoil, we just use this qubits model with ancillary data. That means the potassium 1 meter picon, 1 meter hcon with 80 calibrate samples are enough. And in this, and with calculation, we can get there will be 165.4 tons of lime would be essential, and the total price will be here. But this could be discussed more for the last 2 steps because they'll be more practical. This time we just provide our recommendation. Okay, in this way, I will get my conclusion. In this sugarcane field in Phosphine, yes, we can use easier method such as using the gamma and the EM data to map Cs in different layers. In my study, the optimal model is mathematical model of the qubits, and the sample size is different for 80 for topsoil and 30 for subsoil. And third data, yes, we need to use both the gamma and the EM data, but for different components. But for transect spacing, 5 meters are essential for topsoil, and 6 meters are enough for subsoil. And these results have been published in this journal. And last, I just want to thanks for all you guys in this UNSW Soil Science Central from 2018 to 2021. And I also want to thanks for the generous support from the Soil Science Australia to this conference, and for the support of this project from the Sugarcane Research Australian and HCSL. Thank you. Thanks for all. Sorry, I can't hear that because I just joined here. Can you hear me? How about now? Okay, so may I ask the question because I didn't hear it clearly? You mean nearby area? We just focus on this field for the comparison in this field. We just do a case study in this field. For other fields, I'm currently do some other stuff. So yeah, I just do some other proximate data. So this study just like the case study in this sugarcane field. Okay. Yeah, I'm just wondering the John. Oh yeah, can any other ancillary were? Yeah, I'm answer Jonathan's question. Thanks, Jonathan, for your question. Yeah, we can because currently I'm also doing something about WinNR and maybe some other stuffs to be added for this kind of study. Currently, we may have the EM data, gamma data, and later I'm just doing on the WinNR data and PXRF data to be added. Thank you. Thank you. Thanks so much.
Queensland. And she's going to talk about quantifying wheat yield losses due to soil acidity. Due to soil acidity.
Van Gogh is one of my favorite artists. And here are just two examples of how he brilliantly captured variations within a field and between fields with different shades of green. These spectral variations are also captured in satellite data and can often reveal important information on crop growth. Good afternoon, everyone. I'm Chloe. Today, I'm going to share with you how we used within-field variability to quantify yield losses due to sodicity in northeastern Australia, combining remote sensing, digital soil mapping, and crop modeling. Why sodicity? Australia has the world's most extensive sodic soils, affecting approximately 40% of our land. Various estimates put its cost to Australian agriculture to around 1.3 billion annually. It is essentially a soil chemistry issue characterized by the high amount of sodium ions on the soil exchange complex, but presents both physical and chemical constraints to crop growth. Sodic soils often have poor physical structure and are likely to disperse and erode. Sodic surface soils often hard-set and form crust, which impedes germination and seedling emergence. Sodic subsoils experience decreased hydraulic conductivity, poor aeration, and reduced water storage, hindering root growth and penetration. Sodicity also negatively affects soil solution chemistry. The low electrolyte concentration and the high sodium contents of sodic soils may lead to sodium toxicity and sodium-induced nutrient deficiencies. Moreover, sodic soils are also prone to loss of organic carbon, restricted biological cycling, and can have detrimental effects on soil microbial activities. So how can we quantify sodicity's impact on yield? We predicted yield as a function of sodicity and other environmental covariates. This gave us sodicity constraint yield. Our model predicted actual yield. We then removed its effect from the model to simulate the sodicity rectified yield. The difference between those two gives us the forfeited yield due to sodicity. We studied sodicity's effect on yield in the northern regions of Australia from 2000 to 2016 and split the study period into the wet, moderate, and dry scenarios based on the mean August VPD, vapor pressure deficit. Since it corresponds to the period for wheat and sessis, which is the most critical period for crop growth, we used two empirical approaches to quantify yield losses and compared the results with that produced by the Agricultural Production System Simulator, EPSIAN. We had 676 ESP profiles within the zero cropping land use classes in the northern region. We also had 60 yield maps over the years from 17 farms, which are shown in the figure here. You can see that they do not align spatially. So we investigated two different approaches to harmonize the data and obtain forfeited yield estimates due to sodicity. Previous work often assumed potential sodic constraints to yield at an exchangeable sodium percentage above 6%, irrespective of soil depth. So in our empirical approaches, We also defined our optimum ESP at 0 to 6% and modeled the effects of sodicity on yield using a degree of sodicity variable. The assumption here is that there will be a linear decrease in yield with the natural logarithm of ESP when ESP value exceeds 6. In the first approach, we quantified yield losses due to sodicity at soil sampling locations. The 60 yield maps available to us we first used to train a model that predicts yield using Landsat-derived time-integrated NDVI. That gives us the ability to obtain yield predictions at our soil sampling locations with a modeled that yield as a function of the degree of sodicity variable, climate, and soil texture. We first fitted our model using a machine learning algorithm, QBIST, then refitted the regression parameters in a linear mixed effect modeling framework. In this way, we ensured that no positive effect is associated with sodicity, and we also better accounted for the structure than just using QBIST model alone, because the year and location are incorporated as random effect. And in our second approach, we quantified forfeited yield at the yield monitored locations. So we used increment averaged kriging and basically predicted mapped soil ESP at the global soil map specifications using around 4,000 profiles within the larger region. And combined with the yield monitored maps, our yield maps data, this then is used to fit the same model using yield as a function of the sodicity, degree of sodicity variable, climate, and soil texture. In this way, since all our predictor variables are in a raster format, in this method, we can then use the model to predict across the whole region at the pixel scale, and then averaged the raster to obtain our quantified forfeited yield. This differs from the first approach because since forfeited yield was quantified at soil locations, so we interpolated that data across the region. We also looked at forfeited yield quantification using Epsilon as a comparison to our empirical approaches. This was modeled in a process analogous to the first approach. We simulated yield losses at soil locations with Epsilon, averaged, and interpolated the results for different scenarios. Epsilon uses the AppSoil database to represent soils in Australia. For each ESP profile, if the nearest AppSoil profile falls within 20 kilometers and is of the same soil order, then that AppSoil profile is selected to represent our ESP profile. If the criteria were not met, however, we used an AppSoil profile that is representative for the soil order in the northern region. So the figure in the left actually shows the different representative AppSoil profiles for different soil orders that we used in our simulations. In Epsilon, the effect of subsoil sodicity on weeds were modeled by a function that alters the rate of maximum water uptake per day, the KL factor. These factors vary with different crop and soil characteristics. There are a few caveats to note here. The function only stipulated an effect on yield if on the KL factor. It may or may not affect yield. If the ESP is larger than 15%, compared with the critical value of 6% we used in the empirical approaches. The function was also developed for subsoil sodicity. However, since only 3 of our 600 or almost 700 profiles had an ESP larger than 15% in the surface soil, we contend that this assumption is still suitable for our datasets. I won't go into much detail about how we parameterized epsilon due to time constraints, but we set up our simulations based on the rules outlined here. So what have we found? The empirical approach 1 and epsilon achieved similar forfeited yield patterns for the different scenario, though epsilon predicted a slightly higher forfeited yield, presumably because the epsilon simulations were essentially simulating the difference between a water-limited yield potential and that is being affected by sodicity. Whereas our approach is simulating between model-predicted actual yield and a rectified sodicity, if sodicity is rectified and what the yield improvement might be. An empirical approach 2 predicted smallest yield losses and the largest forfeited yield loss in dry conditions. And these figures are similar with national estimates that puts sodicity's effect on yield in Queensland at around 0.17 ton per hectare, and then in New South Wales, the national estimate was around 0.11. Another thing to note here, since our empirical approach 2 is based on yield monitored data, and these yield monitored data are actually from those top performing farmers. So basically their obtained yield was in the top quintile usually in their SA2 areas. So this is kind of a well-managed land. So you can see that they don't, because that's well-managed, the sodicity effect is really evident in the dry seasons, but the wet and moderate seasons, because of the availability of water, they actually don't have a big forfeited yield due to sodicity. And this is just the map showing that from different approach, how variable our predicted forfeited yield due to sodicity is for different scenarios. And the plot here is actually showing how QBIS, since it classifies things according to rules, and if a certain VPD class is influencing a region, and you might have this bit showing here in the dry environments when the VPD was more evident. And that's the prediction by epsilon approach. So, just like Van Gogh captured the variations in the wheat field with different shades of green, we've captured the yield variations due to sodicity through the 3 different approaches outlined in this presentation. At the soil sampled locations, that is our empirical approach 1 and epsilon approach, this is more suitable to understand regional patterns. However, it lacks the sufficiently fine resolution of sampled ESP profiles to give us within-field variability of how sodicity is affecting yield. And for epsilon, even though it's predicted similar forfeited yield patterns, because of the currently lack of mechanistic details for soil constraints representation in epsilon, and it requires very detailed site-specific parameterization, so it limits its applicability in this type of regional scale studies, whereas we believe that the empirical approach tool would be most suited to model within-field variabilities due to soil constraints, particularly for farms with prior yield maps. And this also because predictor variables such as climate and texture, and they come in increasingly finer resolutions that at increasing accessibility, and knowing the farmers will make it easier to obtain agro-management information that will further help enhance the prediction accuracy of the model. So, in conclusion, that empirical approach tool is best suited to predict within-field variabilities due to soil constraints, particularly for farms with prior yield data. That's all. Thank you very much. Question, please.
We unfortunately have no time for questions, and we have to move on to our next speaker, Kirsten Barlow, mapping the variability of subsurface acidity in southern New South Wales. Have to move on to our next. Move on to our.
Awesome. Well, thanks for coming along today. So I'm going to talk about some work that I've done with my co-author Eva Moffat who was originally at FarmLink, now from Eva Moffat Ag Consulting, around mapping the variability of surface and subsurface pH in southern New South Wales. Now the problem is we know there's a lot of variability within a paddock. So this is a map of grid-mapped surface soil pH, 0 to 10 centimetre. And what we've found through a lot of our work is that across hundreds and hundreds of paddocks, you get at least around 1 unit pH variation across a paddock. So we know there's a lot of variation across that 0 to 10 centimetre soil samples. We also know from a lot of really good research that there's an increasing problem around words have gone. The pH variation as you move down through the profile, and particularly sort of getting acid throttles at sort of 5 to 10 centimetres or 10 to 15 centimetres. So that pH challenge is moving further down through the profile, and as we've moved to a no-till system, we're not incorporating our line amendments, and this problem is increasing. So we know that we've got these two levels of variability that we're dealing with within a paddock. So how do we measure them? What do we do with them? So which of these do we focus on? Do we try and do it all? Do we pick one or the other? Where do we focus? Can we measure them both? And we know we can measure both, but what's economically viable for the farmer? The farmer's not going to go out and measure on a 2 hectare grid 5 centimetre increments down to 20 centimetres. It'd be an awesome data set. As a scientist, that'd be really exciting. But it's not. It's not realistic. So what are the alternatives? Do these surface soil pH patterns of variation actually correlate with what we see in the subsurface? If not, do we know why not? Is it a difference in management? Is it a soil type driver? Is there other factors within there coming into play? Are there other attributes within the soils that we can actually use to guide where we sample, to really help us to target that sampling and get a better understanding of soil acidity within the paddock and therefore better targeted management to ameliorate the problem? So this project looked at 18 growers, 150 hectares of land for each of those growers, 42 paddocks, so some of those were quite small paddocks. So that 2,500 hectares of soil sampling across the region you can see around there, centred around Wagga. The sites were chosen to really reflect a range of soil types, rainfall zones and management histories in that region. The majority of the paddocks had a good liming history. So the majority have been putting a bit of lime in over time, trying to keep up with it. They had no lime inputs over the last 2 years, and the majority haven't incorporated lime. So it's been surface applied, although there's some that have. So what do? The round one of sampling, we went through and we grid mapped. For those that don't know what grid mapping is, we basically do a paddock boundary. We divide the paddock into 2 hectare grids, and then we do a transect sample across each of those grids for a composite sample for analysis. Those samples were analysed for pH and CEC, as well as MIR texture. At the same time, we went around and did a EM38 survey on a 24-metre swath. So really good base data set to understand the variability across these paddocks. Round 2 of sampling, we went through and we went and did 360 strategic segmented soil tests across these. The locations were chosen, A, to include all the paddocks within the data set, but then to capture the level of variation within pH, CEC and EM38 that we saw within that first round of sampling, to try and really capture what are some of those variables in the system and what are the drivers of that variability. So I went through 5 centimetre increments down to 20 centimetres. At the same time, we also did stationary ECA readings and dig stick assessments of visual pH as well. So on to some results. Here's 42 paddocks in one graph. Basically what you're looking at, if you look at the bars first, the orange bar shows you the minimum pH within the paddock up to the average pH within the paddock, and then the blue bar is the average pH within the paddock up to the maximum pH. These paddocks have been ranked obviously based on the average pH, which ranges from about 4.6 up to about 6.4 across the paddock. So big variation in that average 0 to 10 centimetre pH across the data set. On average, most paddocks average about 0.9 pH range within the paddock surface soils, but obviously you can see there's a fair bit of noise around it. The black diamonds then within the graph show the average for that paddock of the 10 to 15 centimetre soil layer. So that's strategic samples, so they're not across all the grids, so it's a slightly different data set, but just to show you sort of where the average of that data set was sitting, you can see that for a lot of those paddocks, the 10 to 15 centimetre average pH is actually sitting below the minimum of our 0 to 10 samples. There's a couple where it sits above. So there's a lot of variation we're seeing within the paddock in both the surface soils and where that subsurface layer is sitting in relation to it. Now if we look at all the segmented samples as a lump, so this is the 360 samples all in together, you can see what we're seeing as a general trend consistent with previous research is the pH in that 0 to 5 is sitting a lot higher. It drops down in that 5 to 10, 10 to 15 centimetre soil layer, and then it's starting to pick up in that sort of 15 to 20 centimetres where the acidification of that system's sort of hasn't quite had the same level of effect. But once again, huge spread in the data. So how do we correlate and understand sort of some of these drivers sitting within the data set? Exchangeable aluminium, mainly a problem in that 5 to 10, 10 to 15 centimetre layer. So this is that pH data again. It doesn't have error bars on it, so please take into consideration that each of these lines is an average of a data set. But the top graph is showing the pH where we've grouped the soil profiles based on the 0 to 10 centimetre cation exchange capacity. So on the point where that strategic sample was taken, the average 0 to 10 CEC was used to group them, and you can see we get a very, very strong movement with the most acidic soils at the lowest CEC, sort of less than 3 up to sort of 7 to 8. And as you see CEC increases on average, what we're seeing is you're getting a higher pH overall. But the other thing you see is that variation down the profile becomes less less obvious, less pronounced as your CEC increases. And that's related to your buffering capacity of your soil, which is related to your cation exchange capacity. Similarly, when we look at the soil texture, so this is based off the particle size distribution from the analysis, you can see that the loamy sands have a stronger variation down through the profile, whereas your clays are a lot more resistant to that change over time. How am I doing time-wise? Okay, so I just want to look at a couple of paddocks a bit more closely to, I suppose, dig into a bit more of the data. So the top left side graph is that one I had up before, and the red arrow shows where this paddock is sitting. So it's got an average pH of 5 in the 0 to 10 centimetre layer, but that varied from 4.5 up to 6.1. So it's quite a variable pH within this case study paddock. The graph underneath that, which I didn't have up separately because I started having too many slides, is basically showing the correlation coefficient between the 10 to 15 centimetre layer and your pH in your 0 to 10, your CEC in your 0 to 10, and the clay percentage in the 0 to 10. So it's picking up some of those. And what we can see is that for this paddock here, the correlation between pH, you might have to take my word for it because it's pretty small, trust me. The pH is pretty well correlated in that subsurface layer to those surface soil properties of pH, CEC and clay content. So there's quite a good correlation across the data set. This map here is, then the graph on the right is showing the individual segmented sample cores that we took on that property, and they've been grouped into two colours. So the orange bars have a CEC of less than 10, and the blue bars have a CEC of above 10. So you can see there's a bit of overlap there, but we're seeing that distinction between your CEC and your pH down the profile is actually being reflected through the data set. If we look at that spatially, you can see if you take the CEC to start with, there's quite a band of higher CEC through here, extending down through here. So you'd expect that to be related to a clay band through the soil. That pattern is very well reflected within the 0 to 10 centimetre surface soil pH data, and it's also reasonably well represented when you look at that 10 to 15 centimetre pH. So that makes it look like it's all going to be really easy, it's all really well correlated, we're all good to go. If we look at case study 2, it becomes less clear cut. So this one here, sitting around there, it's average of pH of 5.2, so very similar average pH to the last paddock. It's ranging from 4.8 up to 5.9 in that 0 to 10 centimetre layer. But what we see in this paddock is that the correlation between the pH in the 0 to 10 is sitting at about 0 and the 10 to 15 centimetre pH. So in this instance, there's actually no correlation between that surface soil pH and what we're seeing in those subsurface layers. So suddenly the story became a little bit harder and a bit more complicated, and that's okay. Once again, though, we see the smaller paddock, so less samples within it, but we're seeing that distinction between the blue lines here where the CEC is above 10, and then the orange ones where the CEC is below 10. So they're sitting about 7 to 9 generally in there. This was a paddock that had quite a good liming history but no incorporation, which you can see here in the fact that the surface soil pH is looking really good in that top 5 centimetres, but it really hasn't moved down the profile into that 5, 10, 10, 15 centimetre layer. So when we look at the spatial maps for this paddock, you can see that the 0 to 10 looks pretty good. I'd be pretty happy with that as a starting point for my paddock if I went out sampling for the first time. But the 10 to 15 centimetre samples are really quite acidic, and there's not a lot of relationship between those pH units, but you can see that the areas in blue in terms of the 10 to 15 centimetre pH do correlate quite well with those higher CEC values and the high clay content within the soil. So it's all around that buffering capacity of the soil and how that links with management, history, incorporation, everything else in terms of the story. So that was a quick run through of quite a large data set with a couple of key points pulled out. It really highlights that lime incorporation, if we don't have that lime incorporation, we're getting that variation in soil pH down through the soil profile. We're getting potential acid throttles developing in that 10 to 15 centimetre layer, which we really want to identify and manage because they're not being picked up by standard soil testing, but they're potentially quite a significant yield constraint within the data set. There's no one size fits all in managing soil pH, I think is probably the key outcome of this. You need to know your soil, your management history, your variability. And I think what this has shown is something like a good sort of understanding of variability in clay content or soil type and CEC can help you target those segmented samplings down through the profile, but they won't necessarily help you understand that 0 to 10 variability. So you need a combination of different tools to manage it over time. Finally, I'd just like to acknowledge and thank the National Landcare Program who funded this work, and once again my co-author Eva Moffat. Thank you.
And
Come and see me.
I haven't seen any questions in the app, so, and we are kind of the end of the time now for that. And I think the session now concludes with that. I don't have anyone else on the list here. I thank you all for attending, and I hope you learned something. And yeah, good luck with the rest of the conference. Thank you.